All right, so hello everyone. Today's lecture is basically going to be about EigenLayer and how EigenLayer works. And the reason we're talking about this in this rollup infrastructure lecture is that a lot of rollup components are currently centralized, and that is a huge issue. And EigenLayer is basically a restaking protocol that can help us solve some of those issues. So let's look at how that can be possible. So first, let's talk about what type of components rollups have. And I think by this point in the lecture series, you might have already developed an understanding of what are the different moving parts of a rollup. So there are definitely sequencers that take the transactions, batch them, and submit them to either a prover, which is again a centralized component, or directly to L1. And then what happened? There are also these things called relayers and bridges that I think you might have studied in another lecture. These basically are also centralized components that convey messages between layers to make them interoperable. So, what exactly is the problem with centralized infrastructure? So, there are basically two major downsides. One of them is censorship. So, imagine that you submit a transaction to a sequencer, and the sequencer does not include a transaction in a batch. So, in case of rollups, you can actually bypass the sequencer directly and submit the transaction onto the layer one, but that definitely requires you to spend a lot of gas, and you should not have to do that, right? Because the entire point of a rollup is for you to seamlessly submit transactions with as little gas as possible, right? So if a sequencer is malicious, if it's trying to censor your transaction, then you have an option to include it, but still it is inconvenient to you. And another thing is definitely downtime. Like, what if the infrastructure itself stops working, it's faulty, or any other problem in its deployment occurred, right? So that way the entire chain can halt, which I think did happen with Arbitrum as well. I'm not sure if the downtime was because of the sequencer or something else, but I recently heard that Arbitrum chain was down for a while. So these are a few problems that happen with centralized infrastructures, which should not happen on blockchains. Like have you might have never heard that Ethereum has suffered a downtime, unlike a chain like Solana. So basically, each rollup has a roadmap to decentralize its infrastructures. So how does it happen? How do you decentralize a centralized component? And the answer of that is simply proof of stake. And I hope that you understand what proof of stake is by now, but let's briefly go through it again. So you have basically a bunch of nodes that perform operations. And there is a fixed algorithm by which they have to perform a transaction. For example, in a sequencer, you take the transactions, and after a certain time, you batch them and submit them onto the canonical chain. That is your algorithm for a sequencer. And the operators, all the operators in this network have to obey that algorithm. There are stakers that basically stake assets and then delegate tasks to nodes. So basically, what you have to do is that these nodes must have an incentive not to cheat, right? So they are asked to put some capital down as basically collateral. And oftentimes, what happens is that these operators, they for doing these tasks, they get rewards on their stake, right? Because like then why would they do it if they don't get rewards? So they get rewards, and people want to get in on these rewards, but they'll also have to perform tasks for that, and not everyone wants to do that. So that's why the staker delegator concept also came along, where there is a group of stakers which provide capital, which provide economic security for a network, and they delegate their tasks to be done by a node or to be done by an operator. And if the operator performs a malicious task, then the stake is actually slashed. So, so yeah, there is some trust assumptions that if you're a staker and you're delegating to an operator, then you must trust that the operator is not going to perform a malicious task. And there is a lot of research going on to mitigate this trust and properly handle the economics of this taker delegator model. But like in an ideal scenario, the node themselves would provide capital. So if their own capital is slashed, they have a very good incentive not to behave maliciously. And so before going into EigenLayer, I want to briefly touch about a topic called token toxicity. and why, like, how is it different from slashing? So there is an argument that a few people would like to make that you don't need slashing in a proof of stake network to have economic security. And the logic behind that is basically that if you are staking some tokens into a network, then it's not some random token, it's the token of that network. If you realize that Ethereum allows you to stake ETH. If you are a node on Filecoin, then you have to stake FIL tokens and so on. Like each proof of stake network, like Chainlink, you have to stake link tokens, right? So the asset that you're staking is of that network, right? So if something malicious happens to that network, like if on Ethereum, let's say an invalid block is finalized, then that is a very huge deal because the entire point of a blockchain, the entire point of a decentralized network is to have permissionless but verifiable and immutable data. And if there is anything wrong with that, if there is anything wrong with this basically proposition, then then what is the point of the network? The value of the network, the reputation of the network will fall drastically. And along with that, the token price of the network will also fall drastically. So that is the concept of token toxicity. That if you're a node and you have some stake in the network, then if you do something malicious, then your stake will decrease in value because the entire network has decreased in value. So uh, you will basically not have a incentive to do something wrong. But plenty of people point out that that is not a right way to think about it, and the answer to that is simply prisoner's dilemma. So here is an example in front of your screen. So let's look at the first table, right? And this is the table where slashing does not occur, and it's a network that basically works on token toxicity. So imagine that you're a node, and you as a node have been given a dilemma that someone has come to you and is asking you to behave maliciously, right? And obviously they'll have to give you some bribe uh, for you to act in not in the best interest of the network. So let's say that you're given a bribe B1 in case the attack is not successful, and you're given a bribe B2 in case the attack is successful. Okay. Uh, so now you'll have to weigh your basically chances of what's going to happen. So you have a stake S, right? And you have a stake S, and on that stake, you're getting a reward. So in case you do not take the bribe and the attack is not successful, then nothing happens to you. You have your stake, and for doing the task, you got a reward. So in that case, you have basically S plus R assets. In case the attack is successful, then you basically do not get a reward because then a malicious transaction has happened and you are not part of that. So you don't get a reward. So you're still left with S, uh, with basically with basically S tick, right? Now let's say that the node did agree to take a bribe. Oh, oh, sorry, I think I flipped the table. So yeah, the token toxicity situation is the one in the bottom table. So what happens is that basically you have a stake and you have a reward, right? And if the attack is indeed successful, then you are at loss, right? Because an attack was happened and you were not part of it. So you lose everything. So you basically get zero if the attack is successful and you did not take a bribe. Now, in case that you do take a bribe and the attack is not successful, then you still get the bribe B1 because that was promised to you. But your stake is not taken away from you. So you still have assets S plus one, S plus B1. And in case the attack is successful, then you get the bribe B2, right? So in this case, B2 must be greater than 0 and B1 must be greater than R. For you to be incentivized to actually do this attack. So now this is not a bad condition to have, right? Like if you're bribing someone, then you have to bribe B2 that must be greater than 0, and you have to bribe B1 that must be greater than R. These are not huge amounts, right? And this is it could be possible for you to actually have this capital and actually convey a third of a network to behave maliciously. So So that's not a good argument for token toxicity. In terms of slashing, as you can see, that if you agree to take a bribe, your stake S will be slashed. So in case the attack is not successful, you get B1, and if the in case the attack is successful, you get B2. So in this case, if you are the briber and you have to provide B1 and B2 values, your B1 must be greater than the stake plus the reward, and the B2 must be greater than the stake itself. And the stake is not a small amount. The stake is like for Ethereum, the stake is 32 ETH. So yeah, 32 ETH is not a small amount, right? So you basically, so if you're the briber in the case where slashing does occur, you have to bribe a B2 that is more than the amount of stake 32 ETH. And if you and you cannot just bribe one single node because then your attack will not be successful. In order for your attack to be successful, you have to bribe more than a third of the network. So in Ethereum, the total staked amount is $100 billion. So if you want to attack a third of the network, then you'll have to basically you need to have a capital of around 35-40 billion dollars, and that is a huge sum of money that we assume that no one is going to spend that much money to attack Ethereum. Because even if they do attack Ethereum, everyone else would know that okay, this is a malicious transaction, and they can just fork the blockchain because blockchains have been forked in the past for far less value, far lesser amounts, right? So that is basically an argument of why something like token toxicity sufficiently is not providing sufficient economic security in comparison to slashing. So now let's actually jump into EigenLayer and understand what it does. A lot. So EigenLayer basically introduced the concept of restaking. So we all know that Ethereum is based on this proof of stake mechanism where nodes on malicious transactions will be slashed, right? And they'll take some amount. So what EigenLayer does is that it allows these validators that already have an amount stake to uh, use their stake, to reuse their stake basically, to secure other networks as well. So let's say that you want to secure Ethereum and Filecoin. You have to provide 32 ETH on Ethereum, and you have to provide the stake amount on Filecoin as well. So you're basically using a lot of capital, right? But what if you use the same amount of capital to secure multiple services? And that is basically the point of restaking, right? So basically, a stake deed is getting additional slashing conditions. So what does that mean? So like your stake deed for Ethereum, the slashing condition would be that you have to attest blocks, and if you attest a wrong block, then your stake will get slashed. On top of that, let's say that you also decide to secure an Oracle service. So what you have to do is you have to provide some Oracle data, some price data, or whatever the Oracle wants to do. And if you provide a wrong price from the average, then you'll get slashed. So the slashed assets will be the same. So like if you have 100 ETH lying around, if you do anything wrong on Ethereum, then the 100 ETH will get slashed. And if you do anything wrong on, let's say, the Oracle, then also the 100 ETH will get slashed. So it has higher risk. But with higher risk also comes higher reward, because then you're also getting, because since you're doing more tasks, you're attesting blocks on Ethereum and you're providing data for Oracle. So you're getting rewards from both of these sources. You're trading risk for reward. You're exposing yourself to higher risks, but you're also getting higher rewards for that. And this is not just any type of risk. This is something called as endogenous risk. And endogenous risk basically means that it is up to you. Like you will not be slashed if you do not do anything bad. At least that is how the system is supposed to work. There are obviously some external risks, like there could be smart contract risks that like let's say the smart contract get hacked. That is an external risk, but with a lot of audits, you can be assured that this is a very minimal risk. And also there could be a risk that the exact slashing condition, that exact slashing condition is not 100% deterministic. So like that is a really big condition for any service, is that if you want to build on a proof of stake network, then you have to be 100% deterministic in pointing out, in identifying who the malicious behaving operators are and who are the honest operators. Because if it is not deterministic, then there will be some external risk for honest operators that their stake can get slashed, and that is something that might be uh, that might be a huge barrier for someone to become an operator, because like if you have some external risk then, and you're also doing tasks, then why would you, then maybe the reward you're getting is not matching with what you perceive the risk is. So these are basically two important factors to consider, and that is basically what restaking is in a nutshell. So now let's uh, go deeper into the EigenLayer's architecture. So as you can see, there they have separated the stakers and operators from each other. The stakers are the people that have the capital and they provide economic security to a service, and the operators are basically nodes that actually to perform the task for the service, right? So there are basically three major components in EigenLayer. One is the token manager, which handles all the assets. One is the delegation manager, which basically handles like who the operators are, what the task is supposed to be. They interact with the middleware contracts and stuff like that. And then there is a slasher manager, which is, as the name suggests, it is responsible for uh, managing that the slashing conditions are verified or not. So, like if an operator is malicious, then someone will raise an event on the slasher manager. It will re-execute the operation, and if it deems the operator to be malicious, then it will slash its assets. And in the token manager, you can see that there are multiple token pools. So that is like the eventual plan of EigenLayer uh, is to not just basically use ETH security. So like validators have to provide ETH on the beacon chain, right? And that is like the beacon ETH that is staked into Ethereum. But not everyone wants to get in on this action. Everyone wants to get rewards from staking, right? But not everyone has like can afford 32 ETH, right? So there is something called liquid staking protocols, and what they do is that, let's say that you don't have 32 ETH, you have, let's say, 1 ETH, or you have 2 ETH, and there are like multiple people who collectively have 32 ETH. So what these liquid staking protocols do is that they take all of this ETH from people, and they combine it and they run a node by themselves, right? And whatever rewards they get, they distribute it proportionately to the stakers. So, uh, what happens is that along with the rewards, they also provide a liquid token to them to basically make the asset make the asset liquid. So what happens is that if the ETH is staked into the network, then it is locked. You cannot use that ETH, right? But what so Lido is one of these companies that does this. So what Lido can do is that it can take like 1 ETH, 2 ETH, 5 ETH from all these people. It will stake it into the network, and then it will create a token out of thin air. Like let's say you give me 1 ETH, so I'll create one ST ETH that represents that, okay, this person has staked 1 ETH with me. Okay. And it can give me this one ST token, which is basically like a receipt that you have given me 1 ETH to stake in the network. So now this one ST ETH does have value because it represents one ETH staked through the Lido protocol, right? So you have simultaneously provided security to the network, and you have also made that token liquid so that it can circulate in the DeFi protocols and generate more yield instead of being locked into a single place, right? And you might think that, okay, that is like that's to duplicate money because like the same asset is being used twice, but that is not nothing new because that happens in traditional banks as well. If you deposit like say 1,000 rupees into a bank, uh, then you can see that your bank balance is 1,000 rupees. But I can go to the bank and I can see that, hey, I want to borrow 800 rupees. And the bank will happily give me 800 rupees from the 1,000 that you gave me. So now I have 800 rupees. And you can see that you have 1,000 rupees in your bank account. So in total, both of us think that we have 1,800 rupees. But in actuality, there is only 1,000 rupees in the bank physically, like 200 in the bank and now 800 with me. So this is basically how money has worked for a very long time. There is a lot of duplication of money and there is a lot of reusing, and like it basically increases the utility of money. And DeFi is just doing what traditional banks have been doing for a very long time already. Uh, so these token pools basically represent all these staked asset classes. So instead of having like redirecting your beacon chain ETH that you have staked, maybe a 32 ETH stake, you're a validator. So instead of putting that into the token manager, you can also put this Lido stake ETH into the token manager, or you can put in Rocket Pool ETH into the manager, or you can put in any other asset. It doesn't have to be restaked. You can also provide assets in general into EigenLayer, which can be used to secure the network. That is not currently that functionality is not currently available. Currently, there are only three tokens, three liquid staking tokens that is available, which is from Lido, Rocket Pool, and Coinbase native staking. But like, yeah, there are plans to expand this uh, such that you can basically use any token or any security to secure the proof of stake network. Then the delegation manager, as I said, it's responsible to manage like which stakers are delegating to which operators, and like whenever you have this service, so these services that are run on top of EigenLayer, like an Oracle service or like any other service, these are basically called actively validated services, AVSs. So these AVSs need to, as I said previously, must have a very defined mechanism to identify malicious behavior. And that mechanism must be this mechanism must be verified on chain, right? Because as I said, it has to be deterministic, and if there is any ambiguity, then that adds external risk for honest operators, which should not happen. In theory, honest operators should have zero risk, right? Like it's not true in practice because there is some smart contract risk and there might be other risks. But as an EVS and like EigenLayer itself, all of these parties are trying their best to minimize the external risk because the the higher the external risk, the more friction or the more uh, conservative operators would be to provide security. And you need to have a high security because, as I said before, is that you have to, if you want to corrupt a network, you need to have a third of the total stake security. So let's say that your network has a total of $1 billion that is staking in your network, right? So you have to own $300 million in order to corrupt a network. That is a big sum. $300 million is a good amount of sum that someone might not spend to attack a network, right? But what if it's only 50 million? Then a third of that would be like around what? A third of 15 million would be somewhere like 16 million or so, right? 16 million it may be true that 16 million that someone can spend 16 million to attack a network and gain hundreds of millions of profit from that. It is possible. So as an EVS or as a protocol, it is in your best interest to smooth the bootstrapping process so that more and more stakers can deposit so that you have a huge economic security backing you, which so that you can be assured that there is no that people are incentivized not to behave maliciously into your network. Yeah, so that is basically the rough architecture of how EigenLayer works and what is the tokenomics behind it. So here is basically like an architecture of how an example of it works, and I'll get to it later because I'd like to talk about why you need to use EigenLayer to bootstrap your network because yeah, that is a lecture. That is what the lecture is about. So you have to decentralize centralized components, right? And in order to do that, you can use proof of stake networks. Instead of having a single sequencer, you can have multiple sequencers. Instead of having a single prover network, you can have multiple provers. And uh, in order to ensure that they're not doing anything malicious, you can use a proof of stake network. You can ask them to deposit a collateral so that they have an incentive to act properly. So how does EigenLayer accelerate this process? And the simple answer is that building a proof of stake network is hard. And it is hard because you have to convince a lot of operators to first come to your network and work for your network. And what's harder is to basically get a stake, is to get the economic security required to have a network that people can believe in, that people can trust, that people can use. Because you need to have a good amount of economic security backing your network uh, so that people can believe that it's functional, right? And that might be difficult because, like, if you're a staker and you see that, okay, this project is coming up and it is building a proof of stake network and it is like launching its own token and stuff like that, why would you put your assets into that network? Because it's not even like you're submitting ETH. You're not putting in ETH because each network has its own tokens. Everyone has an incentive to build their own tokens so that they can control their tokenomics. They don't want to use ETH. Nobody uses ETH for their proof of stake networks, right? So you have to basically trust an entirely new token, and all of this creates a lot of friction. All of this creates a lot of uh, basically barriers to entry, and this is what is this these are the reasons that make proof of stake networks difficult to bootstrap. And the solution to that is that in EigenLayer, you don't have to bootstrap a network yourself because there is already a proof of stake network, the largest in existence, which is Ethereum. Ethereum has $100 billion secured, and there are around 1 million validators that attest block headers, basically attest the entire block and validate Ethereum transactions. So if you can convince them to also run your service on top of that, that is a easier ask than onboarding brand new operators and asking them to stake directly, right? Because as I said, EigenLayer basically allows you to restake the same assets into securing multiple services. So it is also in a way saving a lot of money because as I said that if you have 100 ETH locked up in Ethereum and you have 100 ETH locked up in Filecoin, then you have basically 200 ETH locked up that is not being used to circulate around. Because if money does not circulate, here is a simple concept from economics. If money does not circulate, if money is stationary, if it is locked into banks or it is locked into lockers at people's homes, then the rate of economic growth is going to be less. And there are several economic factors behind that, which is basically that the more the money circulates, the more trade happens, the more innovation happens, and the more prosperous an economy is. And so if you have a lot of services, then these services would demand a lot of Ethereum to be staked and a lot of, not just Ethereum, in general, just a lot of assets to be staked. And that would basically hinder innovation, right? So restaking allows you to use the same asset to stake multiple services. This way, a lot more assets, ETH or a lot more assets can be in circulation. That is one a good thing. That is and the other thing is basically pooled security, because like you're basically pooling security increases the cost of corruption for everyone. So imagine that you are using a DApp, okay, and app has some underlying services that it uses. So it uses Ethereum because it's built on Ethereum. It uses, let's say, Chainlink for its Oracle service, and it uses a bridge, which is, let's say that the bridge is decentralized. Okay, so it's basically using three decentralized components. Ethereum has an economic security of $100 billion. Wow, a lot. That's good. Chainlink, I think, has an economic security of around 800 million. So yeah, 800 million is also a decent amount. But this bridge, let's say this bridge only has an economic security of around 100 million. So what do you think is the economic security of the protocol itself that is using these three services? Uh, and the answer to that question is 100 million. The weakest, the the strongest, like basically the network is only as strong as its weakest link. So it doesn't matter if Ethereum has 100 billion, it doesn't matter if Chainlink has 800 million. The weakest link, the weakest part, which is the bridge, is has 100 million in security. So that is going to be the overall security of the network. And that is somewhat uh, that you might realize that is not a very desirable situation, because if you want equal security for all these services, because in future, because you can already understand that in order to scale blockchain, in order to basically provide the infrastructure for mass adoption, you need to have a lot of different services. And if you want each of these services to be secure, there needs to be a lot of staked capital behind each service, and that could become a huge problem. So that's why that is the reason why EigenLayer is so revolutionary, because it removes this need for each service to be backed by a lot of capital. You can have a huge set of capital, and that single set of capital can provide pool security to each and every user. One risk is obviously that what if multiple of these operators are slashed at once. Like let's say that you're an operator, that you have staked 100 ETH and you are validating Ethereum and Filecoin, let's say. And let's say that you're a bad actor and you do malicious transaction on Ethereum and Filecoin both. Then both of them will come to slash your 100 ETH tokens. But ideally, you should be slashed about 200 ETH, right? Uh, but you're only slash 100 ETH, so only 50 ETH per network. So you must. So some people have this argument that because of restaking, the exact security is diluted, uh, which might be true to some extent, but something like that happening is not very practical. However, you might still want to get some security insurance that okay, even if everything goes to hell, even if everything goes to mayhem, I still have a set of economic security that is mine, that is 100% mine, and that is where something called attributable security comes into play. That is currently being developed in house in EigenLayer, and the basic concept is it's like an elastic it's an elastic demand for trust. So, like, let's say that you're a network and you have a few users. So, you're using the pool security and you have a small insurance of 10 million ETH, along $10 million dollars worth of security on top of the pool security. So, this 10 million of attributable security is yours. So, this 10 million is only going to be slashed if the operators are doing malicious transactions, are doing malicious behavior for your network and only your network. And let's say that your user base increases in the future. What you can do is you can increase this set. You can pay more. So that is where the elastic demand part comes in. You can basically ask for more service and you will be given more service. So like more people can devote attributable security to your network so that that piece of stake will only get slashed if something bad happens on your network and it doesn't has any correlation with any other network. So you're free from the risk of other networks that way. And another thing that EigenLayer is building is something called dual staking. So as I said that each network has an incentive to basically launch their own token because everyone wants to be in control of their own tokenomics, right? And the problem with that is it's basically that the tokens at start are definitely volatile. Why would I secure your network using my assets in your token? So what if the token is volatile? What if it's a pump and dump scheme? Like there could be multiple cases why there are risks associated with a new token. So in order to reduce that, something called dual staking was proposed. And what it basically means is that the network will be secured both by a stable asset like ETH or USDC or something similar, and with a token that the network has created itself. So let's say that there is an Alice network with an ALK token, let's say. So at the start, no one would want to buy the ALK token. So what you can do is using dual staking, you can secure 90% of the network using each and 10% of the network using the ALK token. So you need to hit a quorum on ETH and you need to hit a quorum on the ALK token, and then only a task will be validated. Right. And as time progresses, as your network stabilizes, as you're bootstrapping to a higher level of economic security, and as you're building a community, so people are basically trusting you, and the token volatility decreases over time. You can slowly increase the share of security that your token provides compared to each. So let's say after a few months, you increase it to 20 ETH, and a few months after that, you increase it to 30 ETH, and slowly, you increase the token, your own token as basically to secure the network. So that is also another thing that EigenLayer is working on. These are all the benefits which basically allow anyone to bootstrap a proof of stake network with ease and without any of the constraints that they used to face traditionally. So now coming back to an example EBS architecture. So there's this repository by EigenLayer called the Incredible Squaring ABS. And that is basically like a hello world example of what a simple ABS could look like. So as the name implies, it's an ABS that sends a number to the operators and it asks the operators to square that number and return back. Uh, so basically, yeah, that is the task that they're supposed to do. So let's see like how it can be architected, like how an ABS can work internally. So in the and a disclaimer is that this incredible squaring architecture is something for demonstration purposes. The exact architecture design of any AVS is like highly specific to exactly what that AVS does. So a lot of these components like the aggregator that's written here and the task generator, these are not something that you might find in other AVSs as well. So this is just a very general overview of how it could look like, and it might widely differ based on the exact task and the exact flashing conditions that the AVS that the AVS actually goes through. So in this particular example, there is a task generator, which is like an off-chain component, and it generates basically random numbers at a fixed interval. So what it does is that there is a set of AVS contracts, right? And the task generator basically calls a function on this contract to upload the number on chain. So whenever the number is updated on chain, the operators that are opted into this AVS, they listen to that event and they receive the number from the blockchain, and then they actually perform the transaction. They perform the task. They square the number and they send this number to an aggregator. This aggregator now basically takes all these responses and it aggregates them into a single response, and then it pushes this information on the EVS contract as well, stating that the task is done. And in this process, like if the any of the operators have done any malicious task, then it can call it can talk with the EigenLayer contracts and it can actually slash that operator's state. So here is a more detailed overview of how it works. So you basically have three components. You have an aggregator, you have an operator, and you have the contracts on chain. So in this particular example, the task manager and the aggregator are actually coupled into a single machine, right? So the aggregator spun up basically two threads where the main thread has a task generator. It sends an event to the contract, and like it calls a function which emits an event. So when this event is emitted, the operator has a subscribe thread which basically listens to that event. Now these distributed networks are basically like generally written in Golang, and Golang has some concepts like Go routines and channels. So like Go routines is basically used for concurrency to concurrently execute operations on multiple threads. And channels is basically a communication method that can basically send data from one Go routine to another. So we have the subscribe thread, which basically listens for the events, and through a channel, it sends that data to the main thread, which performs the task. It squares the number, signs the transaction, and then calls the aggregator's RPC thread, which verifies the signature that the operator has sent, and then it aggregates the signature. So now, let's talk a bit about signature aggregation. So if I've ever talked about it in a previous lecture, that Ethereum itself uses something called BLS aggregation, and that is basically a signature scheme which allows you to combine multiple signatures into a single signature. And if you can verify that signature, then you know that all of the underlying signatures are also valid. And this is important because let's say you have thousands or millions of operators, and all of these send you signatures stating that, okay, this is a task that I have done. So here's the signature proving that I have done this task, right? So if you sit down and try to verify all of these signatures, then it's going to take you a long time, because like signature verification is not like a trivial task. It's like somewhat mathematically complicated. So that was actually a problem with Ethereum at like when proof of stake was being developed in the earlier stages before the merge, is that they could have only supported a validated network or a few thousand operators before the scheme was introduced, because that's how expensive signature verification got. And if you wanted a high enough security, then each operator, like to give you a sense of how bad the situation was, each operator would need to have staked around 1500 ETH in order to secure the network. Because if there are only a few thousand operators, and 1500 ETH is like it's a lot of money. So like if I think 1500 ETH at a current price of around, I think, $3,500. It's around $5 million per operator, per validator. That's definitely, that was a very undesirable situation. So that is when Ethereum basically went out and created this BLS aggregation scheme, where you can add all the signatures together, and then you just need to verify a single signature. This allowed Ethereum to reduce the reduce the basically staked amount down to 32 each, which allowed more than which as of today allows around 1 million operators to attest the Ethereum blockchain. Uh, so yeah, that was a technological feat, and that is what is happening here as well in the aggregator, where it is using BLS schemes to aggregate all the signatures. And if it reaches a quorum, because let's say that only one of these operators, let's say, responded, right? You're not going to say that, okay, this task is done and there is a verifiable, like, okay, I have verified okay, that this task is done when only a single operator has actually given you a signature, right? So something that that is not something that you'll consider secure, right? So that's where the concept of a quorum threshold is basically that, okay, if you don't need a single operator's signature, you actually need a multiple operator signature, and there must be a threshold of not operators per se, but like the economic security backing it. So like let's say an operator has staked 1 ETH, another has staked let's say 10 ETH, another has staked let's say 3 ETH, right? So like the sum of all the economic security behind these operators must pass a particular threshold. So you can say that, okay, this task has been done with an economic security of X million dollars, let's say, and that amount should be sufficient enough for you to say that, okay, this condition is indeed verifiable because it's a high enough uh, because it has high enough economic security backing it. And yeah, so if a particular quorum threshold is reached, then the task is marked as completed and the response is submitted on chain. And that is basically an overview of how the incredible squaring repository works. There could be multiple EVS designs. So now let's look at what are the different EVSs that can be built on EigenLayer and how can it help basically roll up infrastructure. So the first thing that comes to mind is definitely decentralizing sequencers, right? So you have a sequencer. The sequencer is supposed to batch transactions. So instead of having a single node run it, you have multiple operators that do these transactions. And if any operator is acting maliciously, then you can just slash them. This solves the situation of censorship because, like, when you submit a transaction on Ethereum, then you don't like you basically give that transaction to a node, and that node gossips the transaction around the entire Ethereum blockchain, right? So you are sure that your transaction is eventually going to get propagated to the block miner. So similarly, if you have a multiple sequences, then if you submit a transaction, it's going to be gossiped around basically all the entire P2P network. And then you can be sure that even if one particular node is malicious, that okay, I will not include a transaction, another node might. So that solves the problem of censorship and also downtime, because if a particular node is faulty or down, then it doesn't matter because there are a lot of other nodes that can pick up the slack. Uh, so that is like a very good argument to have decentralized sequences which can be built on EigenLayer. Uh, Another thing that can be built on EigenLayer is basically data availability. So if you remember the lecture from Avail, they talk about how there are uh, a bunch of nodes that store data temporarily, and these nodes can be built on EigenLayer. And EigenLayer does have a data availability layer called EigenDA that it has developed in-house. On top of that, it can also include fast finality. I will talk more about it in further slides. Another thing that can be built is prover networks. So as I said that in ZK rollups, you basically, the sequencer provides a batch to the prover and the prover generates ZK proofs for these transactions and submits an on-chain. But the ZK prover can, if it wanted, can censor transactions and not generate proof for your transaction. I might remind you again that a ZK prover cannot forge transactions and it cannot generate invalid ZK proofs. That is not mathematically possible. But a ZK prover can censor your transaction and it can be down. So like the entire batch is not submitted because the prover is not working. So again, yeah, a proven network can be built on top of EigenLayer or any proof of stake network. And this will solve both these problems. There is a lecture further in the series that talks entirely about proven networks and proven markets because it's a very complicated and evolving field. And yeah, so we'll learn more about that later. And other things that can be built on EigenLayer are keeper networks or watchtowers. Watchtowers are basically nodes that look for invalid transactions. So, like if you remember the fraud proofs lecture, there in optimistic rollups, you basically assume that every transaction is correct and you submit that transaction on chain. And if the transaction is indeed invalid, then someone can point out that the transaction is invalid, and you can run a fraud proof to like basically revoke that state. So in order to do that, someone has to check, someone has to look. In Ethereum, everyone checks, everyone looks. All the transactions are re-executed by the entire sync, like the entire validator committee per epoch, right? As I said in the finality lecture. But on optimistic rollers, you only need at least a single node, a single operator to rerun the transaction to check if the transaction is valid or not. And if it is not valid, it has to submit a fraud proof. So that is fine for optimism. That is fine for Arbitrum. But if you notice in the ecosystem that a lot of app-specific chains are popping up, a lot of general purpose chains are popping up. And in this ecosystem where there are a lot of different networks and a lot of them might have this optimistic approach, then it might be difficult for these operators to basically rerun every single transaction that happens, right? So you need a set of watchtowers, a set of nodes that specifically rerun each transaction and submit fraud proofs for any invalid transaction in all these chains. So like right now the chains are not that huge, but there is a roadmap, there is a design philosophy, this modular philosophy that there will be several app-specific chains in the future. So there needs to be a bunch of nodes that should rerun transactions and watch if all these operations are indeed valid and submit fraud proofs if they're not. Right. So this is something, this network of nodes is something that can be built on EigenLayer using proof of stake. Keeper networks are same. Keeper networks are somewhat similar in the sense that they do conditions like if then, if this, then that. Right. What that means is that let's say that I submit a transaction on chain and you need to run a script if my transaction is submitted. So you need to basically listen to my uh, you basically have to listen to what my transaction is doing. You might realize that this is similar to what relays do and what I've written here as well, that bridges and relay networks can also be developed on EBSs because what is a relay basically? Like if you want to transfer assets from let's say Ethereum to Arbitrum, you lock your assets on Ethereum. So when you actually lock it on Ethereum, an event is emitted, a centralized bridge or a centralized relay basically listens to that event and it releases assets on Arbitrum chain to your account. Right. That's how you're basically getting uh that is how you're basically getting that. The assets transfer from one chain to another. And then you're locking it on one chain and you're releasing it on another. And that happens through by basically listening to events that happens. Right. So keeper networks are that there is a bunch of nodes that listen to these events and they do stuff based on that event. So for example, let's say that you have a strategy or you have a position on Aave or Compound and your position is close to liquidating, right? So if your position is, let's say your health factor drops below let's say 1.5, then that is that might be an alarming state to be in. So you might have a condition where okay, if this if my health factor drops down, or if let's say my LP position goes out of bounds, or if any particular X condition happens, then I need to take Y action. Okay. And if you run this type of logic on a centralized server, then you might have the downsides of a centralized server that the server might go down, or if the server is owned by someone else, then it may not do that, or it may do something else. Right. And you might not want that. So these keeper networks do that listen to blockchain events and do actions based based on your instructions, these can also be developed as decentralized networks so that you can be sure that okay, I want, if X happens, I want Y to take place, and you can enforce this using a proof of stake network, using keeper networks. And another thing that you can do is basically bridges, which is as I said that okay, You, instead of having a centralized server listening to transactions, you have a decentralized server. So it always, because that is a very problematic thing to have. Like, let's say you lock your funds on ETH, that is irreversible. You cannot change that. That happened on Ethereum mainnet, right? And if the relay network is down, let's say, and the relay network or the relay network is, let's say, malicious, it might refuse to release your assets on the other chain. So that is like a very big concern. And to solve that concern, you can basically decentralize bridges and decentralize relay networks. So yeah, going slightly deeper in, so like data availability. So as I said, that EigenLayer is building an in-house DA called EigenDA, which also hit mainnet a few months ago. And basically, how it works is that the sequencer sends a batch of transactions, and through some math, you're basically dividing that up into multiple chunks, multiple blobs per se, and you send these blobs to operators to hold. Now, these operators have to submit what is called a proof of custody, which basically proves that they are indeed holding this data set, right? And if they're not holding this data set, then their stake will get slashed. So that is where the slashing condition is enforced in EigenDA. And that is how you can basically decentralize the entire DA layer. You can decentralize data availability, which has, first of all, the benefit of being censorship resistant. And you know that this thing is not going to halt. And it also has the benefit that DA itself enables far cheaper gas prices, as was explained in the DA lecture. Another thing that can be built, as I said, was fast finality. So when we were talking about finality, we know that optimistic rollups have a finality of 1 week, right? If you assume that the if you don't believe in their economic security, if you believe that yeah, the economic security is sound, if you believe the fraud proofs are sound, then you might assume that okay, every few hours that the batch is submitted, you get a finality. But that is, as I said, very much dependent upon the economic security that is backing it. So, uh, as you can see that you can build something called a fast finality layer on EigenLayer, which is going to be a proof of stake network that can either give you a soft confirmation where basically you basically attest that okay, this particular information is correct, and you get an instantaneous finality for that transaction. But there will be like a 7-day period where someone can attest, where someone can challenge your claim. And if through EigenLayer, if you can amass a high enough economic security backing the system, then you can basically discard that 7-day period. And you can say that, okay, well, like when I propose the block, that is the final block because I have no incentive to lie because the economic security backing it is too large for me to lie. And another thing, one variation of this could be that previously, let's say Optimism has to attest the entire state of all transactions onto Ethereum mainnet. But now what it can do is that it can send that statement to EigenLayer operators, which can then submit a receipt that that the state is correct on, let's say, a different chain like Arbitrum. And then they can settle they can settle this data on the finality layer, and then they can ensure that there is, first of all, cross-chain interoperability because you have like the data on multiple chains, and you have a finality because there is a lot of economic security backing this network. So yeah, this is basically like an overview of a bunch of roll-up infrastructure that can be built on EigenLayer. And that was it for the lecture. These are a few references that you can look at to learn more about what I talked about in this lecture. So, yeah, are there any doubts or any questions?